Hello and welcome to the video lecture of ME204 Thermal Engineering. My name is Akash James. I'm an assistant professor in the Department of Mechanical Engineering, RSET. This is an introduction to gas turbine power plants or simply gas turbines. This is the sixth module of the course Thermal Engineering. Now, what is a gas turbine? Gas turbine is a heat engine, and like any heat engine, it converts heat to work. Now, heat and work are both forms of energy, but as you have studied in thermodynamics, heat is a low grade energy and work is a high grade energy, and therefore you cannot convert heat completely to work. Some of the heat must be rejected. Now, these two forms two important processes in any heat engine cycle, that is heat addition and heat rejection. Another important process is work production, and work is produced during expansion of the working fluid from a high pressure high temperature state to a low pressure low temperature state. This expansion is happening in an expansion device, which is usually a piston cylinder arrangement or a turbine. To provide the pressure ratio through which the working fluid can expand, we need to have a compression process in the cycle. So these are the other two processes, that is expansion and a compression. To sum it up, every heat engine cycle has the four processes: heat addition, heat rejection, expansion and compression. Coming to a gas turbine power plant, this is the schematic of a simple closed cycle gas turbine power plant. Now here gas enters the compressor and gets compressed to a high pressure state. Heat gets added to the working fluid or the gas in a heat exchanger. Now the heat source commonly is combustion of a fuel. Now the high temperature high pressure gas enters the turbine and expands through the turbine to produce useful work to a low pressure low temperature state. This low temperature low pressure gas passes through a heat exchanger, rejects heat to the ambient condition and is cycled back to the compressor. Now this is a gas turbine cycle. Now for a simple cycle, the turbine is coupled to the compressor so that the compressor is run by the turbine. Now obviously turbine produces more work than is required to run the compressor. Why? Because the working fluid carries the energy that is supplied by the compressor as well as by heat. So the surplus energy that is produced by the turbine we get as useful work. Open versus closed cycle gas turbines. What we have discussed now is a closed cycle gas turbine power plant. Here the heat is added externally to the working fluid via a heat exchanger. What does that mean? Let's say the heat source is combustion of air fuel mixture. The combustion products does not come into contact with or does not mix with the working fluid, but instead the heat that is generated by combustion is transferred to the working fluid via metallic surfaces in the heat exchanger. So it is important to note that the working fluid itself does not undergo any chemical change. The hot working fluid is then expanded through a turbine. The waste heat is rejected in another heat exchanger and gets cycled back to the compressor. So since there is no chemical change in the working fluid can be allowed to complete the cycle. Now let's see an open cycle. In an open cycle gas turbine, fresh air enters the compressor, gets compressed to higher pressure. The high pressure air then is mixed with fuel, and the air fuel mixture is burned in a combustion chamber. The combustion products, which is at high pressure and high temperature, is then expanded through a turbine producing useful work, and the combustion products is then expelled out. Now here the working fluid undergoes a chemical change, and so it cannot be cycled back to the compressor to complete the cycle. That is, the working fluid in an open cycle gas turbine does not complete a thermodynamic cycle, whereas the working fluid in a closed cycle gas turbine completes a thermodynamic cycle. This is an internal combustion engine. The open cycle gas turbine is an internal combustion engine where the working fluid gets combusted, whereas the closed cycle gas turbine is an external combustion engine if the heat source is combustion. Now, compared to an open cycle, a closed cycle gas turbine has several advantages. One is that it can have high working pressure throughout the cycle. This is a closed cycle gas turbine. By using an external compressor, you can increase the pressure in the circuit. By increasing the pressure in the circuit, you are increasing the density of the working fluid. That is, there is more mass of the working fluid circulating per unit volume through the circuit. Now let's say the maximum permissible temperature in the circuit is fixed, then we can add more heat to the working fluid. Why? Because now there is more mass of the working fluid circulating through the circuit, which can carry more energy. So when this mass gets expanded through the turbine, you get more work output. That is, if you increase the pressure in the circuit, you increase the density, thereby increasing the work output. Now, this also provides us with an opportunity to effectively govern a gas turbine. That means, if you want to change the work output of a gas turbine power plant, you can just change the pressure inside the circuit. You can do that by the combination of a compressor and a blow-off valve. Now, if you increase the pressure, you can increase the work output. If you decrease the pressure, you can decrease the work output. This doesn't come at the cost of efficiency, because the maximum temperature and the pressure ratio are not getting affected. Now, increasing the density also increases the Reynolds number and thereby increases the heat transfer effectiveness. Another advantage of a closed cycle is that it need not use just air. It can use other working fluids having more desirable thermal properties and heat transfer characteristics. For example, helium, argon, carbon dioxide, etc. It can also use cheaper fuels like coal. For example, if you are using coal in an open cycle gas turbine, the ash that is carried in the combustion products can erode the turbine blades. But in a closed cycle, since the combustion products does not come into contact with the turbine, the chances of erosion are nil. So you can use cheaper fuels in a closed cycle gas turbine power plant. But the heat transfer to a gas in a heat exchanger is not very practical, because the thermal contact the gas has with the heat exchanger walls is very less. And also, the closed cycle gas turbine loses out to open cycle gas turbines on its compactness. And for these two reasons, closed cycle gas turbines are rarely used. A gas turbine need not be always closed or open. It can be a semi-closed type where there is neither actually closed or open. A typical example is shown. Let's say the air is compressed in two stages. First, in a low pressure compressor, fresh air gets in to the low pressure compressor, it gets compressed. Then it is cooled in what we call an intercooler. And then it passes through a high pressure compressor where it gets to a higher pressure. The gas is then split into two. Some amount of the air is mixed with fuel and is burned in a combustion chamber, and the hot combustion products is passed through a heat exchanger and then is expanded through a turbine to produce useful work. Now the useful work, to obtain the useful work, we can couple the turbine to a generator. Now the rest of the air passes through the heat exchanger, where it gets heat from the combustion gases via heat exchanger. This is then allowed to expand through another turbine, which runs both of the compressors. Now this part of the air does not change its chemical composition, so it can be cycled back to the circuit. So the exhaust gas, the air that can be cycled back to the intercooler, where it rejects heat and then gets back to the compressor. So the air that is passing through this circuit, that is shown in green, completes a closed cycle, whereas the air that is passing through this circuit, where it's shown as orange, is undergoing an open cycle. So this cycle is neither completely open nor completely closed. This is called a semi-closed type gas turbine power plant. The open and closed cycle that we have seen is what we call a simple cycle. Now different arrangements of increasing complexity can be employed to improve upon certain operational parameters of the gas turbine power plant. The first one we'll be seeing is employing a recuperative heat exchanger. Now when the pressure ratio employed in the gas turbine power plant is sufficiently low, the high temperature exhaust gas can be used to heat the air that is coming from the compressor. This reduces the heat that is to be supplied in the combustion chamber, thereby increasing the efficiency of the gas turbine power plant. Now the trade-off here is the increased cost, complexity and weight of the heat exchanger, and also the pressure drop inside the heat exchanger. This is another arrangement. Here the combustion is happening outside of the turbine, so we can use low quality fuels carrying more ash content, because the combustion products is not coming into contact with the turbine blades. The heat of combustion is transferred to the air by using a heat exchanger. Now here we use a single compressor and a single turbine, but instead we can split that up into two compressors and two turbines. In between the compressors we use an intercooler to reduce the temperature. This reduces the work requirement of the compressor. In between the turbines we use a reheat chamber to increase the temperature of the gas. That increases the work output of the turbines. So this can increase the thermal efficiency of the gas turbine power plant. In this typical example, we can also see a recuperative heat exchanger like the one we have discussed here. Now we will be seeing both of these arrangements in detail when we do the thermodynamic analysis of both of these cycles in the next lecture. In the arrangements that we have seen so far, we use a single shaft. The turbines and compressors are coupled to the same shaft. This arrangement is suitable when the load and speed requirement is fixed, like in a base load power plant. But when they are not fixed, like in a peaking power plant or a marine propeller or a gas pipeline compressor, we may have to rely on a different arrangement. Now in this arrangement, the gas is expanded in two turbines which are mechanically separate. The first turbine, which is called a high pressure turbine, is coupled to the compressor and it produces only enough power to run the compressor. The rest of the high energy gas is expanded through what we call a free turbine or a power turbine, which produces the useful work output. Now in this case, the power turbine can easily cope with the varying load and speed requirements, because now it is not dragged by the compressor, since it is mechanically separate from it. Another interesting fact is that instead of the power turbine, if we use a nozzle, we can accelerate the high energy gas, which provides the thrust required to propel the gas turbine power plant and anything attached to it, and that is called a jet engine, and that is what you see in almost all large capacity modern aircrafts. Another arrangement is where we split up the compressor into two and the turbine into two, but without using an intercooler or a reheater. Here the high pressure compressor is coupled to the high pressure turbine by using a single shaft, and the low pressure compressor is coupled to the low pressure turbine by using another shaft. These two shafts are mechanically separate. This is called a multi-spool arrangement, or in this case a twin spool arrangement. This is suitable when the pressure ratio in the gas turbine power plants are very high. And when we are dealing with high pressure ratios, when you use a single compressor, that can lead to aerodynamic instabilities at the final stages of the compressor. To avoid this, we can use a multi-spool arrangement. Here, the two compressors can be run at two different speeds. Advantages of a gas turbine power plant. Most of the advantages listed here are that of an open cycle gas turbine power plant when compared with a steam turbine power plant. As we have studied, a steam turbine power plant requires large structures like boilers, cooling towers, etc. So one of the obvious advantages of a gas turbine power plant is its compactness. It is low in weight, size, and floor space per unit power output. That makes it easier to transport and install, and also the capital cost and installation cost are also lower per unit power output compared to a steam turbine power plant. It takes some time to start up and shut down a boiler in a steam turbine power plant. So when compared to that, a gas turbine power plant is quicker to start up and shut down and faster to respond to load changes. A steam turbine power plant requires large amount of cooling water in its condensers. On the contrast, in a gas turbine, we do not require to cool the exhaust gas back to the ambient condition. So the cooling water requirements for a gas turbine power plant is much less. Efficiency of a simple gas turbine power plant used to be very low. To increase their efficiency, we can always use other methods like by using a recuperative heat exchanger or an intercooler, but that increases the complexity and reduces the compactness of the power plant. But in recent times, with the advancements in aerodynamics and metallurgy, we can use high pressure ratio compressors and high maximum temperatures, thereby increasing the efficiency of even a simple gas turbine cycle. And like a steam turbine power plant, we can use a variety of fuels in a gas turbine power plant. Coming to the disadvantages of a gas turbine power plant, one of the main disadvantages of a gas turbine power plant is its low part load efficiency. This is owing to the suboptimal performance of the compressor at part loads. It is also highly sensitive to component efficiencies like turbine efficiency, compressor efficiency, etc. The efficiency also depends on the ambient condition. We have already established that the work output is proportional to the density, and the ambient condition affects the density and thereby the efficiency. This is especially challenging for aircraft engines operating at varying altitudes. The exhaust losses, that is the energy that is lost with the exhaust gas, is really high. We can always reuse this energy by using a recuperative heat exchanger as shown before, but only at the expense of increased cost, complexity, and reduced compactness. The compressor work required is proportional to the specific volume. Since we are dealing with gas, the specific volume is really high and the compressor work required is high. This is when compared with a steam turbine power plant, where we need to compress or pump a liquid where the specific volume is much less and therefore the work is less. It requires air filters Now coming to the applications of a gas turbine, one of the main advantages that we have listed is the compactness of the gas turbine power plant, and for that reason we use it mainly for aircraft propulsion. The jet engines that you see below the fuselage in a large aircraft is basically a gas turbine power plant. It is also used in marine propulsion, where the lightweightedness and compactness is more important than efficiency. It is also used in gas and oil transmission pipelines. It is used in power plants in many ways. One, as a peak load power plant. Here in the picture you can see a steam turbine power plant along with a gas turbine power plant. You can see that a gas turbine power plant is much more compact than a steam turbine power plant. Why peak load application? Because a gas turbine power plant can quickly adapt to load changes compared with a steam turbine power plant. So typically a steam turbine power plant is used as a base load power plant, where it supplies a constant load at higher efficiency, and when there is a peak requirement of load, the gas turbine power plant steps in. Now in some cases, gas turbine power plants are used as base load power plants. As we have said, the cooling water requirements for gas turbine power plants is much less, and so when the availability of cooling water is less in a particular location, we may choose a gas turbine power plant as a base load power plant. And due to the above said reasons, it can also be used as an emergency power plant. And since it is compact, easy to transport and easy to install, it is a preferred choice of power in offshore platforms. It is suitable for combined cycle power generation. What does that mean? Here in this particular example, the gas turbine power plant and steam turbine power plant are separate. Instead of that, they can be used together in a combined cycle operation, having much more thermal efficiency than either of them separate. A typical example is when you use the exhaust gas of the gas turbine power plant in a heat recovery boiler to generate steam for a steam turbine power plant. Another application is cogeneration. Cogeneration is, apart from generating power, you can use the high temperature exhaust gas of the gas turbine power plant for processes in an industry. It can be used directly, or it can be used to generate steam that is required for a process industry. Now let's do a thermodynamic analysis of a gas turbine cycle. Gas turbine cycles can be grouped broadly as shaft power cycles and aircraft propulsion cycles. Now a clear distinction between the two is that the aircraft propulsion cycle depends significantly on the forward speed and altitude. We here will be discussing only shaft power cycles. We will see the ideal gas turbine cycle. The following are the assumptions made in an ideal gas turbine cycle. First of all, the compression process and the expansion process are assumed to be reversible and adiabatic. We assume that there is no irreversibility due to friction. This may not be the case for an actual process. We also assume that there is no heat transfer to or from the system. Since the compression and expansion processes are fast processes, there will not be enough time for heat interaction with the surrounding. So the assumption that the processes are adiabatic are more or less correct. Now if the process is reversible and adiabatic, then that means it is as an isentropic process. Why is that? Because if there is no irreversibility due to friction, there is no entropy generation. And if there is no heat transfer, there is no entropy transfer through the system boundary. Now since it is a steady flow process, the entropy of the working fluid that is coming in and leaving are the same. Now, keeping all this in mind, we can say that the entropy of the working fluid does not change during the compression and expansion process. That is, these processes are isentropic. Now, coming to the heat transfer process, heat addition and heat rejection, these are the assumptions made. We assume that first of all the heat is transferred externally. That is, we assume that there is no internal combustion. The heat is transferred externally via a heat exchanger. And the heat transfer itself is reversible. That means the temperature difference through which the heat is transferred is infinitesimal. Also, we assume that there is no pressure drop during the heat addition process. In an actual case, this may not be true. There may be pressure drop. Also, the process definitely is not going to be reversible in an actual cycle. The change in kinetic energy of the working fluid between the inlet and outlet of each component is negligible. That must be the case if the compressor and turbine are working efficiently. Then we assume that there is no pressure drop in any of the parts of the working fluid, that is the inlet, ducting, combustion chamber, heat exchanger, intercooler, etc. We assume that the working fluid composition doesn't change throughout the cycle. This must be the case if the heat is transferred externally. Now, if it is an internal heat addition process, we know that the working fluid composition does change, but we assume for ideal cycle this is not the case and the working fluid composition is not changing throughout the cycle. Similarly, we assume that the working fluid is an ideal gas and the specific heats remain constant throughout the cycle. Now, we know that the specific heat will increase with increase in temperature, but for an ideal cycle we assume, for simplicity of analysis, we assume that the specific heat remains constant. Also, we assume that the mass flow throughout the cycle is constant. Now, this is not the case for an open cycle where we add fuel in the combustion chamber where the mass is increased, but in an ideal cycle we assume that the heat is transferred externally, there is no internal combustion, so the assumption is that the mass flow of the gas is constant throughout the cycle. And finally, the heat transfer in any heat exchanger is complete. Now, heat exchanger, we may employ a heat exchanger to add and reject heat. Here we assume that the heat transfer is external, so there must be a heat exchanger for heat addition and heat rejection. There can be also heat exchanger for recuperative purposes, as we have discussed earlier. Now, in all the heat exchangers, we assume that the effectiveness of the heat exchanger is 100%. That is, since the working fluid is the same, the temperature drop of the hot fluid is equal to the temperature rise of the cold fluid. Now, this is the schematic of a closed cycle gas turbine. We will try to draw the TS diagram of an ideal gas turbine cycle. We assumed that the compression and expansion process happening in the compressor and the turbine respectively are isentropic processes. Now, an isentropic process in a TS diagram is a vertical line because the entropy remains constant. The working fluid is cycled between the minimum entropy in the compressor to the maximum entropy in the turbine. When you add heat, the entropy increases from the minimum value to the maximum value, and when you reject heat, the entropy reduces from the maximum to minimum value. So the compression process from 1 to 2 corresponds to the minimum entropy, and the expansion process from 3 to 4 corresponds to the maximum entropy. Now, coming to the heat addition and heat rejection, we assume in an ideal cycle that these two processes are happening at constant pressure. So it is important to see what is the nature of a constant pressure line in a TS diagram before we can draw the line. So from the thermodynamic relations we have studied, we know that dH is equal to TdS plus VdP, and since the pressure is constant, dP is equal to 0, so this term vanishes and dH is equal to TdS. And since this is an ideal gas, dH is equal to Cp dt. If you equate the right hand side of both these equations, you will get Cp dt is equal to TdS. By rearranging the terms, we can write dou T by dou S at constant P is equal to T by Cp. Now dou T by dou S at constant P is nothing but the slope of a constant pressure line in a TS diagram. Now we have seen that the slope is equal to T by Cp, or the slope of a constant pressure line in a TS diagram is proportional to the temperature because the specific heat is constant. Now from this equation we can also infer that the variation of temperature with entropy when pressure is constant is exponential, and two constant pressure lines will diverge from each other. So that answers our question how a constant pressure line can be expressed in a TS diagram. A constant pressure line will be an exponential curve. Now there are two pressures involved in the simple cycle. The heat is added at the maximum pressure in the cycle and heat is rejected at the minimum pressure in the cycle. The working fluid is compressed from minimum pressure to maximum pressure in the compressor and is expanded from maximum pressure to minimum pressure in the turbine. So there is a maximum pressure curve, an exponential curve corresponding to the maximum pressure, and another exponential curve corresponding to the minimum pressure. These two lines are diverging from each other because if you take at a particular entropy, the slope of this curve is proportional to the temperature, which is higher than the slope of this curve, which is proportional to the temperature corresponding to it. So the slope corresponding to the entropy, the particular entropy for a minimum pressure will be less than that of the maximum pressure, or in other words, these two lines will be diverging from each other. Now let's go from state to state in the cycle. Let's start with the state 1. In the state 1, the gas is at minimum pressure and at minimum entropy. So this is state 1. So let's mark it. This is state 1. And when you compress, the compression process is assumed to be isentropic. So the entropy remains the same as minimum, but the pressure increases from minimum to maximum. So the process is like this, vertical, and it reaches the maximum pressure at this point. So this is state 2. Then heat is added at constant pressure. The pressure is not changing. So when heat is added at constant pressure, it is going to trace out this line until it reaches the maximum entropy corresponding to the entropy of the expansion process. So this is state 3. From there, it expands through the turbine isentropically. So it is going to follow the vertical line until it reaches the minimum pressure, that is at this point. So this is state 4. Then from 4 to 1 passes through the heat exchanger, rejecting heat at constant pressure. So once again, from 1 to 2 is an isentropic compression process. From 2 to 3, constant pressure heat addition. 3 to 4, isentropic expansion, and 4 to 1, constant pressure heat rejection. So this is the TS diagram of an ideal gas turbine cycle. Isentropic compression, in which we supply work in the compressor. Constant pressure heating, where we add heat. Isentropic expansion, where useful work is obtained, and constant pressure cooling, where heat is rejected. An ideal gas turbine cycle is also called as a Brayton cycle. So what we have drawn now is the TS diagram of the Brayton cycle. This is the TS diagram we have just discussed. Now let's see how to draw the PV diagram of the Brayton cycle. Now the process 2 to 3, that is the heat addition or the heating process, and process 4 to 1, which is the cooling process, are constant pressure processes. In a PV diagram, a constant pressure process will be a horizontal line. So there is a horizontal line corresponding to the maximum pressure, and there is a horizontal line corresponding to the minimum pressure. Then the expansion and compression processes are isentropic. So what is the nature of an isentropic curve in a PV diagram? It is given by this equation: PV raised to gamma is equal to constant. So corresponding to the minimum entropy, we have a curve corresponding to PV raised to gamma is equal to constant, and corresponding to the maximum entropy, we have another curve following the same equation. So these two curves are also diverging when you go down. Now let's start from state 1 before compression. It is at minimum pressure and minimum entropy, so this is the state 1. So this is state 1, and it is isentropically compressed to state 2. So it follows this curve to the maximum pressure at this point, that is state 2. Then heat is added at constant pressure until it reaches the maximum entropy at this point. So this is state 3. Then it is expanded isentropically following this line to the minimum pressure at this point, that is state 4. So 1 to 2 isentropic compression, 2 to 3 constant pressure heat addition, 3 to 4 isentropic expansion, and 4 to 1 constant pressure heat rejection. This is the PV diagram of a Brayton cycle. So what we have discussed now is the TS diagram and PV diagram of a Brayton cycle or an ideal gas turbine cycle. This is for a simple cycle. Let's start thermodynamic analysis of a ideal gas turbine cycle by writing down the steady flow energy equation for the compression process, that is a process from state 1 to state 2. This is a steady flow energy equation. This is basically an energy balance for the compressor. The left hand side represents the energy that is coming in, and the right hand side represents the energy that is leaving. Energy is coming in the form of heat and the energy carried by the mass, and energy is leaving in the form of work and the energy carried by the mass at the exit. Energy carried by the mass is the sum of specific enthalpy, kinetic energy per unit mass, and potential energy per unit mass. Now also note that the work term is negative here because work is being done on the compressor rather than being done by the compressor. Now, the change in kinetic energy and potential energy across the device is assumed to be negligible, so we cancel those terms. The compression process, as we have seen, is assumed to be adiabatic, so there is no heat transfer during the process 1 to 2. The rest of the term, when we rearrange it, we can write it like this. That is the rate of work done per unit mass flow rate. We will get it as kilojoules per kilogram. The rate of work done is in kilojoules per second. Rate of mass flow is in kilogram per second. So what we get is not a rate term, it is in kilojoules per kilogram, or the work done per unit mass. We get it as H1 minus H2. If you multiply by negative 1, we will get W12 as H2 minus H1. We have obtained the compressor work input during the process 1 to 2 per unit mass, that is W12, as a change in enthalpy during that process. It can also be written as specific heat times a change in temperature, because we assume that the working fluid is an ideal gas and hence obeys the relation dH is equal to Cp times dt. Now, since the specific heat is constant, assumed to be constant, when you integrate this equation, you get delta H is equal to Cp times delta T. When you apply the steady flow energy equation to the heater, you obtain the heat input per unit mass, that is Q23, as a change in enthalpy during that process. It can also be written as Cp times delta T. Similarly, the work output per unit mass in the turbine W34 can also be written as a change in enthalpy during that process. It can also be expressed as Cp times delta T. We define the pressure ratio Rp as a ratio of maximum to the minimum pressure, and if you refer back to the Ts and Pv diagrams of a simple Brayton cycle, you can see that P2 and P3 are equal to the maximum pressure and P1 and P4 are equal to the minimum pressure. We define another term, maximum to minimum temperature ratio, small t. It is equal to T3 over T1 because T3 is the maximum temperature in the cycle and T1 is the minimum temperature in the cycle. This can be easily seen in the Ts diagram of the Brayton cycle. The compression process is isentropic and hence we can write T2 over T1 as P2 over P1 raised to gamma minus 1 by gamma, or simply Rp raised to gamma minus 1 by gamma, where gamma is the ratio of specific heats. On similar lines, you can write T3 over T4 as Rp raised to gamma minus 1 by gamma because 3 to 4 is the isentropic expansion process. Now, for convenience of the ensuing derivation, we write this as Y. The thermal efficiency of a heat engine is defined as the net work output per unit heat supplied. Now, the net work output in this case is the turbine work output minus the compressor work input. Now, the turbine work output per unit mass, the compressor work input per unit mass and the heat input are all derived by using the steady flow energy equation. Now, if you substitute these terms in the equation for efficiency, you get this. Now, if you write T2 in terms of T1 by using the ratio Y and T3 in terms of T4 by using the ratio Y, this expression changes to this one. Now, if you do a little bit of rearrangement and cancellation, it is easy to obtain efficiency as 1 minus 1 over Y, where Y is Rp raised to gamma minus 1 by gamma. And hence efficiency of a simple Brayton cycle we have derived it to be 1 minus 1 by Rp raised to gamma minus 1 by gamma. Gamma, remember that is the ratio of specific heats and it is a property of the working fluid. So the efficiency depends on gamma as well as the pressure ratio. So for a given working fluid, we can say the efficiency depends only on the pressure ratio. And if you increase the pressure ratio, the efficiency increases. Now for the same pressure ratio, if you are using a different working fluid with a higher value of gamma, you have increased the efficiency of the cycle. Now this is possible for a closed cycle. It is not possible for an open cycle. And for an open cycle, the working fluid is always going to be air, where the gamma is 1.4. Now, another important parameter is the specific work output, that is the work output per unit mass or the net work output per unit mass, and that is equal to the work output in the turbine per unit mass minus the work input in the compressor per unit mass, both of which we have derived by using the steady flow energy equation here. Now if you write T4 in terms of T3 by using the ratio Y, you get this. It is always convenient to write the specific work output in a non-dimensional form as W net by Cp times T1. Here note that Cp is a constant and T1 in most cases is the ambient temperature. And this is equal to T into 1 minus 1 over y minus y minus 1. This can be easily obtained from this expression by dividing this throughout by Cp times T1. Please try that out. Now that means the specific work output, or the non-dimensional form of the specific work output, is equal to T times 1 minus 1 by Rp raised to gamma minus 1 by gamma minus Rp raised to gamma minus 1 by gamma minus 1. So it is important to note that the net or the specific work output depends on the pressure ratio as well as gamma, just like the efficiency. But unlike the efficiency, it also depends on the maximum to minimum temperature ratio. Let's rewrite the equations for efficiency and specific work output. In this slide, we will see how these two quantities vary when you vary the pressure ratio. The minimum possible pressure ratio is 1, and you can clearly see when the pressure ratio is 1, the efficiency will become 0, and so does the specific work output, because this term vanishes and this term also vanishes. That is, when the pressure ratio is minimum, that is when it is equal to 1, the efficiency and specific work output will be 0. Let's see that in a TS diagram. The cycle 1, 2, 3, 4, 1 represents the simple Brayton cycle, where 1 to 2 is compression, 2 to 3 is heat addition, 3 to 4 is expansion, and 4 to 1 is heat rejection, as we have discussed earlier. Now the temperature corresponding to state 3 is the maximum permissible temperature in the cycle, and we consider that as a constant. The area enclosed by a cycle in a TS diagram, as we have studied, represents the net heat transferred in the cycle. We have also studied that the net heat transfer must be equal to the net work transfer in a cycle. That is, the area enclosed by the cycle in a TS diagram also represents the net work output. Now let's see how the variation in pressure ratio affects the net area and so the net work output. When the pressure ratio is reduced, the temperature after compression is reduced. That is, the state 2 will be lowered in a TS diagram. State 2 will be lowered on this vertical line because the compression is still an isentropic process. When you reduce the pressure ratio, state 2 will be lowered until it reaches this point where it coincides with state 1. That happens when the pressure ratio is 1. That is a minimum possible pressure ratio. Again, when the pressure ratio is 1, the states 1 and 2 will coincide. So the heat addition process, which is a constant pressure process, will trace out this constant pressure line until it reaches the maximum temperature at state 3. Since the pressure ratio is 1, states 3 and 4 also will coincide, and the heat rejection process from 4 to 1 will also follow along the same line. That means the heat addition and heat rejection are now represented by the same line. In other words, there is no net area enclosed in the cycle. That means there is no work output in the cycle. That is what we have discussed here. When the pressure ratio becomes 1, the net work output becomes 0. Now, if 1 is the minimum pressure ratio, what is the maximum possible pressure ratio? Now, when you increase the pressure ratio, the temperature at state 2 will increase. So, state 2 in a TS diagram will rise along this vertical line. And how far it can rise? Only up to the maximum permissible temperature in the cycle. It cannot increase further. The pressure ratio during compression process, we know, is equal to T2 by T1 raised to gamma by gamma minus 1. P2 by P1 is equal to T2 by T1 raised to gamma by gamma minus 1. Now, when the pressure ratio is maximum, the temperature at the end of the compression will be equal to the maximum possible temperature in the cycle, that is T3. So Rp max is equal to T3 over T1 raised to gamma by gamma minus 1. That is a maximum permissible pressure ratio in the cycle. Now if you increase the pressure ratio further, the temperature after compression will be greater, which is not permissible. Now when the pressure ratio is maximum, the states 2 and 3 will coincide. Why? Because we cannot add further heat. The state 2 and 3 will coincide because we cannot add further heat, because when you add further heat, the temperature must increase. That is not permissible. And when states 2 and 3 coincide, the expansion process 3 to 4 will follow along the same line as the compression process 1 to 2. So once again, the net area enclosed by the cycle will be 0, and hence the net work output also will become 0. That is when the pressure ratio is maximum, the specific work output will be 0. Now the maximum pressure ratio is T3 by T1 raised to gamma by gamma minus 1. We know that T3 by T1 is nothing but the small t. So when pressure ratio is minimum and pressure ratio is maximum, the specific work output is 0. Now let's see what happens when the pressure to the efficiency when the pressure ratio is maximum. If you substitute this quantity in this equation, we will get efficiency as 1 minus 1 over small t. That is, interestingly, the efficiency of a Carnot cycle operating between the same maximum and minimum temperatures. Now theoretically we can say, when the pressure ratio is maximum, heat is added at a constant maximum temperature and heat is rejected at a constant minimum temperature. Now the heat added and rejected are, we assume it to be infinitesimal quantities. In that case, the efficiency will become the Carnot efficiency. Efficiency is equal to 1 minus 1 over T. That is same as the Carnot efficiency of the cycle operating between the same maximum and a minimum temperatures. Now let's plot this equation in a graph of efficiency versus pressure ratio. Now it is clear that when the pressure ratio increases, the efficiency increases. It's also clear that when the gamma value is higher, the efficiency will be higher. Gamma is 1.4 for air, gamma is 1.6 for argon. So if you are using argon instead of air, you will have higher efficiency for the same pressure ratio. And what are the limiting cases? We have just seen there is a minimum pressure ratio and a maximum pressure ratio. The minimum pressure ratio is 1, and when the pressure ratio is 1, no matter what the value of gamma, the efficiency will become 0. And there is a maximum pressure ratio. This will not go on to increase forever. There is a maximum pressure ratio where you get the maximum possible efficiency, that is the Carnot efficiency. So that is a limiting case. So when gamma is higher, it will reach the Carnot efficiency faster than when the gamma is lower. That means when gamma is higher, the efficiency, Carnot efficiency is reached at a lower pressure ratio than when gamma is lower. Now let's see the same for a specific work output. Now in this case, efficiency depends only on pressure ratio and gamma. So in our graph, there are only these three variables: efficiency, pressure ratio and gamma. But for a specific work output, it depends upon the pressure ratio, gamma as well as T, that is the maximum to minimum temperature ratio. So when you draw a graph, it must be for different T values. When you draw a graph for specific work output against pressure ratio, it has to be represented for different T values and different gamma values, and different gamma values are not represented here. t values are represented. This is for t is equal to 2, this curve is for t is equal to 3, and this curve is for t is equal to 4, and this is for t is equal to 5. Here at the limiting cases, when pressure ratio is minimum and maximum, what happens? In both cases the specific work output becomes 0. So when pressure ratio is minimum, that is when it is equal to 1, no matter what the value of t, no matter what the value of gamma, the specific work output will be 0. Now when pressure ratio is t raised to gamma by gamma minus 1, then also the specific work output will be 0. So this value, this point will be different for different t values. The pressure ratio at which the maximum pressure ratio will be different for different t values, as is clearly visible here. So all these curves are going to meet the x-axis at some point. Now, since the specific work output and at minimum and maximum pressure ratios are 0, the work output will be maximized at a point between these two pressure ratios. The pressure ratio corresponding to that we will call the optimum pressure ratio. So the maximum specific work output is this. Corresponding to that we have a pressure ratio that we will call as the optimum pressure ratio. This will be there, an optimum pressure ratio will be there for all the t values. Now how to find out the optimum pressure ratio? Now it is very obvious that to find out the inflection point, what we have to do is take this equation where the specific work output is expressed as a function of pressure ratio, differentiate this with respect to the pressure ratio and equate that to 0. And the pressure ratio corresponding to that is the optimum pressure ratio. Now since that is a little bit tedious, we will use a simpler equation which we have written earlier. Here instead of Rp raised to gamma minus 1 by gamma, we use the variable y. Now if you differentiate this equation with respect to y, we will get an optimum value for y, from which we can find out the optimum pressure ratio where the specific work output maximizes. I urge you to try that, and the value that you will get is this. The optimum pressure ratio is going to be t raised to gamma by 2 gamma minus 1, that is the square root of the maximum pressure ratio. The optimum pressure ratio is the square root of the maximum pressure ratio for a simple Brayton cycle. Now if you substitute this value in the specific work output equation, you get the maximum specific work output, and it is going to be root t minus 1 the whole square, where small t is the maximum to minimum temperature ratio. Similarly, the efficiency corresponding to the optimum pressure ratio, which we can call the optimum efficiency, will get as 1 minus 1 over root of t. Again, t is the maximum to minimum temperature ratio. I also urge you to try this. This is an easy derivation. It is also interesting to see that at the optimum pressure ratio, the temperature after compression and the temperature after expansion will be same. Let's try that. From this equation we can see the optimum pressure ratio raised to gamma minus 1 by gamma is equal to root of t, that is root of T3 by T1. But the pressure ratio raised to gamma minus 1 by gamma is also equal to T2 by T1. It is also equal to T3 by T4 for this simple cycle. Now let's say this is A equal to B equal to C. Then B multiplied by C must be equal to A squared. That is T2 by T1 multiplied by T3 by T4 should give you T3 by T1. Here T3 and T3 will cancel, T1 and T1 will cancel. What remains is T2 by T4 is equal to 1. That is T2 is equal to T4 for the optimum pressure ratio. In other words, the TS diagram states 2 and 4 will lie on a same horizontal line. At stage 2 and stage 4, the temperature will be same. That is a condition for maximum work output. That is it for this lecture. We will meet again in the next lecture. Thank you.